Alright, so for this experiment, you're going to need just a handful of items. You'll need your assorted wires. You'll need this particular module here that has 3 resistors on it, and this module here that has just a single resistor on it. And what I'm going to show you is the difference between resistances in series and resistances in parallel, and how to measure resistors. Now, resistors do several things in a circuit, and on a circuit board they allow us to step down voltages from where they are. Because they resist, they basically use up some of the electricity that's in the circuit and allow us to take a single power source and manipulate it down to lower values than what exists there. So if we need something, for instance, that operates off 20 volts, but then somewhere else in the circuit we need 12 volts, rather than having to have 2 different supplies, we're able to take and add resistors and potentially other components to allot for that lower voltage need. Now, on this particular resistor card, if you look, your resistor should have 3 values embossed into the plastic. And on this particular one, again, it may vary with the kits, but we've got a 5 ohm on the bottom, a 10 ohm in the middle, and a 15 ohm here. So the very first thing is I want you to measure those. And so I've set my meter, and you don't have the cheaper version meter of this in your kit. You'll have to use the multimeter. And we're going to try and measure each of those. So this is our 15 ohm, and we can either measure on the resistor or at the lead sites here. I'm going to remove these little caps to make it easier. So I'm going to go down in here and measure, and we see we're reading 15.2 ohms, and that's varying a little bit, and I can dig in and change that, but basically we're reading 15 ohms plus some change. So let's go down in here and we'll read, and this one should be reading about 10, and it is, and this one should be reading about 5 or so ohms. Now, the reason we're reading some of this value, reading about 5.6, even our leads had some resistance, but we can tell an obvious difference between the 15, 10, and 5, which is the main thing that I wanted to do. So let's talk about resistors in series versus resistors in parallel. Now, most everything that we plug in, well, not most everything, but virtually absolutely everything we plug into our homes are plugged in to what we call a parallel circuit. So obviously resistance is the opposition of the flow of current. So everything we plug in that uses power has a resistance to it, and it depends on if that resistance is very low, we use a lot of electricity. If that resistance is higher, we use less electricity. And that just makes sense because if we're providing electricity a path that's easy, then it's going to flow very well, which means our meter is going to turn very fast. If we provide electricity a path that doesn't flow quite as well, then our meter is going to turn a little bit slower. And if we provide no path at all, which is infinite resistance, maximum resistance, then there's no flow at all. So if I unplug something from the wall, then that where that was is now at maximum resistance, and there is no flow. So let's first take a look. If you remember, we had a 15 ohm, a 10 ohm, and a 5 ohm resistor. Now I'm going to attach those in series. Now when I say that something is in series, what that essentially means is we have a resistor here, and I'm just going to draw a cardboard box, a square. I don't know why I said cardboard box, but we'll let that represent our 5 ohm. And this drawing upside down is really fun. And then we'll add in a 10 ohm. A little easier to do a 10 than it is a 5. And then we'll add in a 15 ohm. So that represents each of these three here. So let's see if I can draw a 5 without making it backwards. I think that's right. So if I have to go through all three of these resistors, I'm encountering the resistance of this guy, plus the resistance of this guy, plus the resistance of this guy. So you can somewhat think of it as standing in a line. Let's say you go to the Disney World, and this line to use your coupon is 15 minutes long. You're going to have to go through that line. And then this line to get your ticket is 10 minutes long. And then this line to actually get admitted is 5 minutes long. You're encountering each of those. So in essence, you're going to have 15 plus 10 plus 5. That's the way resistances in series work, because there's only one path I can add up those resistances. Now, it's not really related to time. I just use that because it kind of makes sense, because electrons are trying to flow through these three when we add them to the circuit. So there's going to be some resistance here that they have to go through, here and here. And time makes a real good analogy, but it's not really a time-based thing, so I don't want you to be thinking in those terms. So right here, I have a 15 ohm, a 10 ohm, and a 5 ohm. Well, obviously, let's label this B for black, and let's label this R for red, and we'll label this one B for black, and we'll label this one R for red, and we'll label this one B for black, and this one R for red. So we've got to have a starting point, so I'm going to make this the black one. And then we've got to go through the resistor, out of the red into the black. So I'm going to make that connection. It's a little bit wonky the way I'm doing it, but you'll get the idea. So I'm going to connect a path from this red here to that black. So bear with me while I'm tightening that. So basically we would start here, go through here, come around that way, and go through the red, which is right here, into that black. So let's do that also. So coming around into here. So we're doing it a little bit zigzag. We could have done it a little bit different way, but that's okay. So we're coming out of our black, or starting out our black, I should say, going through that resistor to our red, coming out of that red into this black, going through that resistor into this red, coming out of that red, excuse me, I didn't mean to scoot the whole thing, into this black, going through that resistor and coming out here. So now this point right here is right here, and this point right here is right here. And I should measure 30 ohms or somewhere thereabouts right there, and I do, 30.2. So we've proven that what I talked about here is true. We're going to look at a little bit different outcome here if we wire these in parallel. So let me grab another piece of paper. Parallel is like this. We have a 5 ohm, a 10 ohm, and a 15 ohm. So this is our 5 ohm, it's our 10 ohm, and this is our 15. I think I drew that backwards, didn't I? Maybe not. Nope, I didn't. Again, drawing upside down. So what we're going to do, and we'll call this black, whoops, I definitely drew that upside down, black, 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 and red, red, and red. We're going to connect all our blacks together, and we're going to connect all our reds together. So we'll go from this black to this black. To the bottom one. Apologies for sliding the papers all around. We're going to make sure those are good and tight. Not super tight, but tight. And I'm going to have to pause the video. Okay, so I went ahead and tied the red side together. I added this black and red lead. And what I essentially did is what I'm showing you here in these drawings. I attached all the reds together on this side, and added this wire out here. So these 4 points are all electrically the same. This is electrically the same as that, which is electrically the same as that, which is electrically the same as that, and that. Same over here, same as that. So now, unlike series, remember when we had them all in series, we had no choice. The electrons that were flowing through these 3 had to go through the first, then through the second, then through the third. However, as electrons enter from this side, they get a choice. They can go through here, they can go through here, or they can go through here. So it's kind of like checkout lanes at Walmart. Once we're kind of standing out here, we assess which ones are valid paths, and we choose different routes. Now electrons excuse me, do that based on physics and the resistance of these. Now something unique happens here. We added up all those resistances because we had to go through them all. So we had to add the amount of resistance this had to that and to that. But we don't have to go through, or the electrons don't have to go through all of these. But something really interesting happens when we parallel resistances. The overall resistance goes down, so current is more able to flow, and the more we add, the lower it gets. And the really neat thing is our overall resistance here is going to be lower than our lowest, and we had a 15, a 10, and a 5. So these 3 resistors in parallel, I can absolutely guarantee you will be lower than 5 ohms. It may only be 4.9, it may be 2.5, we could calculate that, but it's definitely going to be lower than our lowest value. So for instance, if this were 100, and this were 100, and this were 10, we're going to be lower than 10. If this were 1,000, this were 500, and this was 5, we're going to be lower than 5. Again, that could be by a large amount, or it could be by a very small amount. It just depends on the value of all the resistors in conjunction with one another. So what I'm going to need you to do is, there's going to be some questions you have to answer, but the picture I need from you guys is a picture of these 3 wired in parallel, very similar. Make sure your student ID and your name is on a piece of paper in that picture, or your badge will suffice. Also, you're going to end up needing this extra resistor here. There's going to be some questions based on using that resistor and doing some configurations there. And you'll need to understand if we say add something in series versus add something in parallel. So again, if we're putting them in series, we have to go out of one into the next, out of that one into the next. But in parallel, basically we hook all the left sides and the right sides together. So if I were going to parallel this one, I'll make it where the red isn't the same, even though there's no polarity. I would have to add a wire from here to here and here to here, and we wouldn't have to change this wire because it's electrically connected. So make sure you understand the terminology of series and parallel. So just as I said, I think in the previous part of this video, parallel is just like our homes. When we plug stuff in to outlets in our home, all those outlets are wired in parallel. And the more stuff we plug in, The lower the resistance gets and the higher the current flow, thus the higher the electric bill. Start unplugging things, our resistance increases, so less current is going to flow and our power bill is going to go down, which is a good thing. So that's the difference between parallel and series. And again, don't forget your picture that you need of this, and there'll be some questions related to this. We may have you wire just a couple of these in parallel. We may have you add this. We're just going to ask you various questions about these resistors and maybe what some are in series and so forth. So be prepared to look at a schematic and be able to wire it. And when I say that, what I'm talking about is if we say, for instance, here's a resistor, and we'll call it 15 ohm, and I'll turn this around where you can see it, and here's the 5 ohm resistor. We may say wire those two in series and measure the voltage, measure the resistance, or we may say wire those two in parallel and measure the resistance. So if they're in series, we'd have to enter one, come out of it, and enter the other. If they're in parallel, we would have to put these two sides together and put these two sides together and measure what they measure in parallel. So again, a difference between series and parallel, need to understand that. If you have questions, please let us know.